Hello, my name is Jack Lewnard. I'm a program director in the Department of Energy's ARPA-E agency. I'd like to discuss a proposed program we call Remedy. Remedy is focused on addressing anthropogenic methane emissions. We're interested in methane because it's a powerful greenhouse gas, more than 20 times as impactful as CO2. So we're considering funding new approaches that could prevent methane emissions, destroy methane at its source, and even considering options to remove methane after it has entered the atmosphere. Addressing methane emissions complements greenhouse gas programs focused on carbon dioxide. One interesting aspect of methane is that natural processes scrub methane from the air. As a result, we don't need to cut anthropogenic methane emissions to zero. If we can cut these emissions by 10 to 30%, we can start reducing the amount of methane in the atmosphere quickly. This slide shows the global methane balance. Annual methane emissions are about 558 million tons. Natural processes consume about 548 million tons. So the accumulation in the atmosphere is about 10 million tons per year. If we can cut anthropogenic emissions by more than 10 million tons per year, we can begin to reduce the concentration of methane in the atmosphere and its contribution to climate change. Remedy's approach is to focus on systems. By systems, we mean products or processes that can quantify the methane emission reductions and has sufficient sensors or instruments to allow control and advise if they are not operating properly. ARPA-E is looking for solutions, not just research programs to study a technology. Our goal is to eliminate methane, so oxidizing it to CO2 is perfectly acceptable. It's not necessary to make a high-value product. There are already many programs focused on converting methane, particularly flared natural gas, to high-value products, and we don't want to duplicate those efforts. We anticipate the economics for Remedy technologies will be based on carbon trading, so it's essential to have accurate measurements of methane reductions as part of any system. The systems can use any technical approach. We anticipate that many approaches will be required given the diversity of methane sources. And since methane sources can vary in concentration and flow rate, the processes need to be flexible and robust. ARPA-E likes to focus on hard problems, so we'll share some thoughts about why we think this is a challenging area. First, there are literally millions of sources, which we'll discuss further on the next slide. There's a lot of uncertainty about methane emission rates. Methane concentrations and flow rates range over several orders of magnitude and can vary even at a single source. The methane concentration is usually below the lower flammability limit, so it's too dilute to burn on its own. However, in some cases, the concentration is too high to burn, so it needs to be diluted with air to ignite. Methane's chemistry doesn't help. The molecule has a high degree of symmetry, making it very stable and hard to react. It won't ignite until the temperature is about 600 C. The result is that Remedy doesn't expect to find the silver bullet that works for all sources. Each approach has its challenges. For example, sealing mines and wells requires materials that can last for hundreds or even thousands of years. Oxidizing methane to CO2 will likely require catalysts and/or additives to promote reactions and possibly do mechanical designs or catalytic reactors. Biological approaches need to consider microbial consortia, nutrients, and the possibility that methane emissions may have other species coincident with the methane, which are poisons to the biology. We mentioned the diversity of methane sources and the need for better emission measurements. There's many studies on this subject and new detecting techniques to identify and quantify sources. One interesting trend is that in many cases, a relatively few number of super emitters often accounts for a majority of the methane emissions. Some sources, such as cattle, which are responsible for enteric fermentation methane emissions, have relatively small emissions per cow, but the number of emitters is large, estimated at about 95 million cattle in the U.S. So these cattle account for the largest single source of methane in the U.S. emissions inventory. Then there's an unknown number of orphan wells, both oil and gas, which may not be properly plugged. Some estimates are as many as upwards of 3 million. Even some properly sealed wells can leak, and those are then there are as many as 2 or 3 million of those types of wells. There are over 30,000 gas-fired compressors that slip about 1 to 5% of the methane that is used to fire these compressors, and over 50,000 flares which slip probably between 1 to 2% of their methane when running properly, and potentially a lot more depending on wind and other factors. Methane also escapes from thousands of coal mines and landfills. The National Academies published a thorough report on methane emissions, sources, and measurements techniques about a year ago. We recommend downloading the report. It's free from the NAS website shown here. So, what are approaches that could work? Well, ARPA-E is looking for you to propose novel solutions. However, here's some examples which are not intended to limit your creativity nor indicate a preference on our part. So let's start with ruminants. Cattle don't need methane to grow. In fact, methane represents a loss for both the animal and the farmer. There's been many proposals to look at modifying the feed, the microbiome in the gut, and the cattle themselves. ARPA-E is interested in new approaches or perhaps combination of approaches. For sealing mines and wells, we may be able to get insights from solutions developed for the nuclear waste storage industry, which also requires materials to last for thousands and even upwards of tens of thousands of years. There's a long history of developing catalysts to control VOCs, or volatile organic compounds, and many efforts to catalytically partially oxidize methane to high-value products. Perhaps some of these research efforts in developing new catalysts can be extended to methane. And finally, we're very interested in enhancing nature's processes for scrubbing methane from the air. The chemistry and the biology are understood. What's needed are innovations to accelerate these processes. Here's how we will assess concepts. ARPA-E recognizes there's lots of programs on methane reduction, and so we're not looking for incremental technology improvements. For example, the industry is very active right now looking to reduce things like compressor rod leakage and improve operating and maintenance practices to reduce the amount of methane purged from valves. We're instead focused on novel, disruptive approaches that can dramatically impact the cost and or performance of techniques to abate or prevent methane emissions. These technologies should reduce methane emissions by somewhere between 30 to 50% for areas where there are no prior art that would instruct a meaningful comparison. So, for example, enteric fermentation or landfills, where there really isn't a precedent for methane removal from those sources, or by up to 99% where there are good precedents. For example, flares have a nominal destruction efficiency of at least 95% today. VOC catalysts are often more than 99% effective in removing VOCs. So we're looking at two different criteria for the reduction, and we also expect the methane removal technologies to be cost competitive with carbon capture. They must not cause other environmental problems, such as emitting unacceptable amounts of NOx or air toxics like formaldehyde. So we're constraining the solution to be something that would be practical and economic. Again, we want to see a systems approach. It's not enough to study a particular technology, say a catalyst or a biological technique. The technology must be packaged as a solution, including quantification and control. ARPA-E likes to fund teams. We're looking for teams with diverse skills, and ideally ones that have a commercialization partner as one of the members of the team. And finally, ARPA-E's mission is to de-risk new technologies. So we'd like to see a program plan that concludes with a relevant lab-scale test or ideally a limited field test. We hope this webinar has sparked your interest in the Remedy program. Please feel free to contact me or Maruthi, who is helping you with the program development. We have already issued a request for information, and we have had a workshop on October 20th. As part of the outcome from that workshop, we're also putting together a teaming site to help participants identify potential partners for their proposals. There's also information on the blog, as well as frequently asked questions about ARPA-E contracts, and you can contact our contracting officer directly if you have questions about submitting proposals to ARPA-E. We hope that you will consider developing a novel approach for methane abatement and prevention, and thanks for your time and your interest in the Remedy program.